This meeting is being.
Okay, so there was one problem which was left from the previous session. We didn't have time to finalize it. I don't know how many of you have thought about the problem. Any? So that was the problem, if you remember. So we were supposed to factorize this polynomial, and then we just learned one technique for factoring polynomials, and that was finding the highest common factor common to all the terms in the polynomial and pull it out. Yes? Okay, so what is the obstacle here? The only problem that you need to be careful in this problem is this, to see that immediately we see that this is a product, because this is y minus 2x times y minus 2x, so that's a product. This is also a product between 2x and this factor as a whole. This is also a product. And then I want to find a common factor which is common to all of them. Of course, it is clear that y minus 2x is common here and there, but this is not exactly y minus 2x. So in principle, I cannot say that y minus 2x is a common factor to all of them right now. But there is a little bit a difference between 2x minus y and y minus 2x. We also had this in Math 1C, if you remember. If something like this happens, so you know that if there is no difference between a plus b or b plus a, they are exactly the same. So let me write them here for you. So we always know that if a and b are real numbers, a plus b is exactly equal to b plus a. But this is not the case for a minus b and b minus a. They are not the same, yes? For example, if you have 3 minus 2, the answer is 1. But if you have 2 minus 3, the answer is minus 1. So they are not equal. But there is a connection between these two. So you see the answers are opposite to each other. So a minus b is minus b minus a. So this is something I want you to remember. Whenever you want to whenever you want to interchange the summands, the numbers that are added together, you don't have any problem. You don't need to be careful about the order in which you bring the numbers in. But when you have subtraction, you have to be careful, because if you do it the other way around, you get an extra minus sign. So a minus b is equal to minus b minus a, minus brackets open b minus a. So whenever you want to interchange the places where these numbers appear in a subtraction, you can do that, but the price that you need to pay is an overall minus sign for all of it. Okay, but of course, if you want to write a minus b, I can change them by bringing the signs. I can write it as minus b plus a. That is also correct, because if I ask you what is the sign of a, it's positive here, it's still positive, and the sign of b is negative here, it's still negative. So that is also correct. It is not wrong. But what we want to learn here is this: whenever I need to interchange the roles, the numbers, the order in which the two numbers appear in a difference, you need to remember yourself about this rule, which is of course very simple and it's understandable. If I ask you, take this pair of brackets, you say that I will multiply this minus sign here, it becomes minus b, which is correct, and this minus sign will be multiplied by this negative sign, it becomes positive a, which is also correct. So remember this fact. So before starting factoring this polynomial, I need to do this change. Okay, so now can you help me? The first, I just copy and paste the first two parts because I know what I'm going to do here. Okay, but now can you tell me what should I write for the last term according to this explanation?
Plus y.
Plus y and then?
And then within brackets, positive y minus negative,
2x.
minus 2x.
Exactly. Thank you very much. So I just, if you don't understand, please interrupt me and let me know just by talking, not by chat. I cannot see the chat window. So what we have done, let me explain. Instead of this expression, the reason that I got motivated even to do this in the first place, because I see that there is a very small difference between these two. So I cannot factor anything out in this form. So this will remind me of this rule. In my head, I would say, okay, there is no difference between this expression. I can put a minus sign here and I interchange them. But of course, this minus sign will be applied by this minus sign. On this minus sign, this becomes positive, as Gustav mentioned. Now, everything is in order. You see, I have y minus 2x, which is a common factor. So I pull it out, and based on what we learned before, I have to put them in pair of brackets. Then I open a bigger pair of brackets. So there were two factors of y minus 2x available here. One of them is pulled out, so one of them is left. So let me still keep the pair of brackets. And then from the next one, I had three factors, this one, and this one. One of them is pulled out, so two of them, 2 times x is left. And from the last one, just y is left. But of course, no one writes this in this form because this factor in its own can be simplified a little bit more, yes, by removing this pair of brackets. This pair of brackets is of course necessary because this is packaging all what is inside it, and then we are supposed to multiply the whole expression by this. So this pair of brackets around this is necessary, but we really don't need to have this pair of brackets here. So let us remove that, because always simplification is a very vital part of the calculation. So I remove this, it becomes y minus 2x plus 2x plus y. But again, I will not stop here because something interesting happens here. This term and this term are similar and opposite, so they will be canceled. But these two terms are similar and they will be added together. So this becomes equal to y minus 2x, but y times y, sorry, y plus y is just 2y. And I don't write these pair of brackets if I write it in this way. I would write 2y first, and then I would write y minus 2x. It's better to write it in this way. Of course, if you write it in this way, that's also correct. But this is more beautiful from my point of view. Okay, so this was what was left from the previous session. Then I want to also put a remark here for you. So let me make it bigger. So this is important. I want you to remember this because, of course, factorization is a very extensive lesson, but what you need to learn is just we will finalize factorization this lesson. But I just want you to know about this. Let me write this remark. This factoring method of factoring the highest common factor, if applicable to all the terms, you see I have written all in italics, I'm emphasizing on it. If applicable to all the terms involved in the polynomial, has priority over any other method that we will learn in the coming sessions. Later, I will present examples to illuminate the content of this remark that I want to talk about this today. Okay, so we learned the first trick to factorize a polynomial, and that is to distinguish, to recognize actually the common factor, the highest common factor common to all the terms of the polynomial, and pull it out. Today, I want to teach you two more techniques for factoring polynomials. Then I am just mentioning that, remember this remark, that this method that we learned just now is has the priority over the other methods that are coming. So first of all, if I give you a polynomial, you first need to think, is this method of pulling out a common factor is applicable? If that's the case, you pull the factor out, then start thinking what you can do with the rest of the problem. So this is the meaning of priority. It becomes more clear when I give you more examples. Okay, so today I want to teach you this. So if you remember, we had a squaring pattern, and that was a plus b. We had two versions for a squaring pattern, and that is a squared, if you remember, which was crucial not to forget to write this middle term 2 times the first one times the second one, and then plus the second one to power 2. We also had this, let me write the same size. So a minus b to the 2 is equal to a squared. The only difference is that now we will have minus 2ab plus b squared. And then we also learned a conjugate pattern, and the conjugate pattern was a plus b, for example, times a minus b is equal to a squared minus b squared. Now here you see immediately that these two patterns are also very useful, if applicable, of course, to factorize some particular form of polynomials. Why is that? If I ask you, is this in factorized form, you should say either it cannot be factorized at all, or it is not a factorized form because this is not a product, this is a sum. And then let me just remind you here, you might think that I can pull a out from here. Yes, you can, but let me pull it out and let us write it here. I just want to test your understanding. If I pull a out from the first two, because there is no a in the last one. So if I intend to pull out a, I have to take these two and pull out a. So what happens? This becomes a plus 2b, but what is left at the end is b squared. Now, this is very important. I want you to really understand this. If I ask you, do you agree that this is a factorization of this expression? Do you agree or not? If not,
Yes
why?
and no.
Yes? Which
It's
one?
you have factorized the part of the expression, but it's still not a product.
Okay, so the answer is yes or no, definitely. Which one?
Well, in that case, I'll say
So
no.
your explanation is correct, but what is your conclusion at the end?
I think it's a sum and that it's not finished.
Exactly. So it's not a factorized form, exactly, because if I ask you read this expression, you will never read this as a product. You say that this is the sum of these two expressions, even though each one of these expressions are in the form of a product. But if I ask you read this, you cannot say this is a product, that's a sum. And when you say that that's a sum, it's not a factorized form. So I just want you to understand, if I give you this expression and I ask you to factorize that, even though you might think that you are doing right, yes, you are factoring this part, but the whole expression is not in the factorized form. Okay, so I just want you to understand this. Okay, let me clean this one now. Okay, but now you can see the answer. If I ask you, how can you factorize this? Because you realize this method that I just described was not correct. But now if I ask you, how can you factorize this? Do you have any answer for me?
You take out both a and b.
Is it possible?
I think so.
No.
How is that possible, Gustav? So can you just tell me how should I do that, and I will write it for you here.
Well, you remove 1a from a squared and 1a from 2ab.
Yeah, so this becomes this.
Exactly. And
then there's a b squared left. But then I cannot do that because b is in the prison of these two pair of brackets, so it's not free so that I can pull this b out. So this is not working.
Okay.
Even if I start with pulling b out, then a squared will be left. Yes, I can pull b out, then it would be a 2a plus b. But again, for the same reason, this is not a product yet. So these two, I want you to understand why these methods are not correct. And now I want to say what is the correct one. Actually, the correct one is on the screen now. What is the factorized form of a squared plus 2ab plus b squared?
I guess it's a plus b squared.
Yeah, exactly. So why? Because first of all, you know this equality is right. On the other hand, if I ask you, do you believe that a plus b to the 2 is a product? You would say yes, because this is another name for this product. So any power itself is also in a product form. So that's the answer. So when I want to answer this, factorize this, so you need to recognize the pattern, and if the pattern is exactly this pattern, you can immediately collect it back to the answer. So this is why again you see that factorization is more or less the opposite operation of the reverse operation of expansion. When I say expand this, you would write this answer. But now if this is given to you and we ask you to factorize it, it means more or less to put it in the original form of a product. So this is why when I was teaching about squaring patterns, I wrote this on the left and this was the answer. And now when I want to teach you the same pattern but in the form of a factorization, then I would write this one on the left and then I would say this is the answer. So you see that is nothing new at all. Okay, and then you need to understand. So for example, if you have this pattern, if I ask you what's the factorization of this, immediately you will say a minus b to power 2. So this is today's lesson. You need to learn how to do this the other way around. And the same thing here. If I ask you factorize this, what is your answer? Here we don't have anything in common at all, so that I cannot pull anything out, but can I still factorize this? What's the answer?
Yes.
Yes.
Yes?
Yes.
Okay, so what's the factorized form of a squared minus b squared, everyone?
A plus b
B.
bracketed and a minus b.
Exactly. So you see
Yeah.
that is nothing new at all. So I just write it the other way around. When I have this, but this is important to recognize the patterns. Okay? Recognizing this pattern is very simple. So you have something to power 2, another thing to power 2, and then they are subtracted from each other. So this pattern, you should have it in mind. When you have the difference of two complete squares, this is the conjugate pattern, and then you can use the formula for the conjugate identity to factorize that. How? You would say, I will take the square root of the first one, and I will take the square root of the second one. Once I add these two answers, once I subtract them, and then multiply them. It's easy. But for this one is also easy, but there are 3 terms involved here. How should I recognize the pattern? First of all, you see that 2 complete squares are in my, first of all, you see that I have 3 terms. So let me see. I have 3 terms, 2 complete squares, 2 complete squares. So if you don't mind, let me write them properly. So for the first one, let me give it a name, number 1, and then number 2. Okay, so for number 1, what I have 3 terms. Yes, 2 of them are complete squares. And the important thing is that the middle one is 2 times the square of the square root of one of them times the square root of the other one. Yes. So the important thing is that the middle one, the middle term, is 2 times the square root, the product of the square roots of these complete squares. Okay, so this, of course, you don't need to memorize these things, but you need to have this in mind. Whenever you see, by the way, a polynomial having 3 terms is called trinomial. Trinomial. A polynomial consisting of 3 terms. So when you want to use this pattern, somehow you need to have 3 terms added together 2 of them should be complete squares, but this is not still enough. The middle term should be 2 times the square root of the first one times the square root of the second one. Whenever this happens, then you have a squaring pattern. Okay, and for number 2, let me, of course, I will give you a lot of examples now, but let me just also have this one. For the conjugate pattern, you should have the difference of 2 complete squares. So if I want to give you a very simple example, for example, is this a squaring pattern or not? How should you think about this? First of all, you have 3 terms involved. Okay, so 3 terms involved. That's correct. The second thing is that 2 of them should be complete squares. Is that true? Yes. X squared is x to power 2. 1 is another name, 1 for 1 is 1 squared. So then x squared is the complete square term. 1 is also a complete square term. So I have also this one checked. But the important thing is that the middle term is 2 times the product of the square roots of these complete squares. You need to go to a scratch paper, for example. Take the square root of this one, it becomes x. Take the square root of this one, it becomes 1. And then 2 times, you see it is written 2 times the product of these squares. You multiply a 2. What is the answer? The answer is 2x. And this 2x is exactly the middle term. So this means that, yes, everything is according to the pattern. I have 3 terms, 2 complete squares, and the middle term has exactly the same property. So this means that, yes, this is a squaring pattern. So the answer is what? The answer is the square root of the first one, the square root of the, I will take the square root of these 2 complete squares. One of them is x, the other one is 1. But then I see this sign. Yes, do you remember? If the middle term is positive, this should be positive. If the middle term is negative, this should be negative. So what happens is that here I put a positive, then of course I have this power of 2, so this becomes this power of 2. So when I ask you factorize this expression, it is completely wrong to factor x out, because let me just do it again. If I factor x out, this becomes like this. If you put this equality, I 100% accept it from you. Equality is, from equality point of view, it is true, because that is completely exactly equal to this expression. But is this in factorized form? No, because this is still a sum, not a product.
Also, I have a question.
Yes, please.
So can't we say x and then times in parentheses x plus 2 plus 1 over x? So 1
okay,
as a
but that is not a factorization. Yes, you can do that, but that is not a factorization. Because if you remember, I told you that you are not allowed to use fractions unless it is mentioned. You remember, I told you that by default, we always factorize without fractions. So
but
when
if
you
the
pull
fraction
out,
is an integer as well. So if you think
no,
that
this fraction is not an integer, it is sometimes
but if
an
it's
integer.
like 6 over 2, that's equal to 3, so that could be an integer.
If I ask you 6 over 2 is an integer, yes, that is an integer, but 1 over x is not always integer. If 1 over x, for example, x is equal to 1, yes, you are right. 1 over 1 is an integer, but most of the time 1 over x is not an integer. For example, if I choose x2, x equal to 3, all of them are fractions.
Yeah, but in case that one happens, can I use this kind of method?
No, because it's still, this is a variable. Because if this is a variable, you don't know the value. So you are not guaranteed that this is not a fraction. But if you say this equality is true, I 100% agree that this equality is true.
Okay, thank you.
So what you have written, this one is equal to this one, is true. But this is not a factorized form because there is no guarantee that this fraction is an integer.
Yeah, I see it now.
Yeah. Okay, and then let me go to the other one, for example, to the conjugate pattern. So for the conjugate pattern, for example, I can tell you some very simple example. Of course, I will give you more examples. Is it possible to factorize this, for example? I have 4x to the power of 2 minus y squared. Is it possible to factorize this? First of all, you see that I have two terms and then the difference of two complete squares. Yes, this is a difference, first of all. And 4x squared and y squared, both of them are complete squares. Why? If I want to write all the details, instead of 2x to the power of 4x to the power of 2, I can write it in the form of 2x to power 2, and then I have minus y to the power of 2. So you see that this is a complete square because it is a power of 2 of some expression. This is also a complete square. It is the second power of y. And this is the difference of two complete squares. So this means that this exactly fits the pattern. So what I do, I open two pair of brackets. I take the square root of this one, which becomes 2x. I put it here and there. And then I take the square root of this one, which becomes y. I put it this here and there. One of them should be positive, the other one should be negative. Which one you choose to be positive, which one to be negative is completely arbitrary. It doesn't matter. Yes? So that is also the conjugate pattern. So the only thing that you need to train your eyes to be able to detect these patterns immediately, even if they are in disguised form. Yes? So yeah, the simple problems are really simple to recognize, but the harder problems are the problems that you need to train your eyes so that you can catch the patterns. So that is the whole point. And let me just remind you about the remark. So you see that we learned this method in the previous session, pulling the highest common factor out. Then today we learned two other methods using these rules. With this remark is telling you that the previous method, if applicable to all terms, has priority over these two. Again, I will give you examples so that you can understand this better. Okay? So now let me go to the next page. I want to pause the video and give you this exercise. And then I want to wait for you so that you can solve the problem first. So let me see which one is that. Yes, this one. Okay. So this is the question. I am asking you, so this is important, distinguish for which of the following polynomials the squaring pattern is somehow applicable and factor them. Okay? So I think, I don't know, how 1, 2, 3, 4, 5, 6, 12. So I can give you, let me divide it in two parts because this is two. I want to make sure that you understand. So let us do these 6 parts. They are very easy. And I give you 8 minutes, okay, up to part F. Then I will come back and just try to see that if you are following the correct path or not. If not, I will correct you, then we will continue, okay? So from part A to part F, I will give you 7 minutes from now.
Okay, but so if I understand, the squaring pattern works for all of them, we just need to find how it works. Is that
No,
what we're supposed to do?
so you need to check them. Some of them does not follow. Actually, one
Okay.
of them, I think, does not follow. I want to be alert about this point. Okay, I don't want your brain be conditional without be conditioned without understanding what is going on. Because, for example, let me tell you what I mean. People, by seeing this, they say that, okay, I have 3 terms. This is completely square. This is completely square. So let me write the answer. This, yes. I want to force you somehow to check if the middle term is also in the correct form, okay? If that is the case, factorize it. If not, just leave it blank, okay?
Yes. So if
Okay, so could you solve the problem? There was, I think, one of them that doesn't follow the pattern. Could you recognize that? Which one?
Yeah, I think it's F.
Yeah, F doesn't work. Exactly. Thank you. So let me just try to solve these problems here for you. So part A. So first of all, let me just explain. How should I realize that there is a possibility that this can be factorized using the squaring pattern? This is important. Of course, here now our lesson is about the squaring pattern. So most of the examples that I am providing, of course, is related to the squaring pattern. But the point is that if you go further and further, for example, if you are doing something in a very different context, this is up to you to realize, to recognize that this pattern is a squaring pattern. This is why I want to repeat this. So if I want to solve this problem, so for example, I can open a scratch paper for myself here. So what do I have? I have 3 terms, the first point. Then I have 2 completed squares. As soon as I see 3 terms with 2 completed squares, I get suspicious that this might be the squaring pattern. But then I need to do a very simple calculation in scratch paper or in my head. I take the square root of the first completed square, x squared becomes x. I take the square root of the second completed square, 4 becomes 2. I multiply them, and I multiply by a 2. Always by a 2 because of 2ab, yes? The answer is 4x. If the answer turns out to be exactly the middle term, then this means that this is actually the pattern, and then I can solve the problem. So I would of course, if you don't write it, I don't want you to write this in the exam. If you write the correct answer, that's correct. But if this is not the pattern and you are mistakenly using the pattern, then it would be wrong. Okay, so if I want to do this, then I would put a pair of brackets with power of 2 here. I take the square root of this one, which is x. I take the square root of this one, which is 2. And then I check the middle term. If it is positive, I put positive. If it is negative, I put negative. So here I have to put positive. So what I expect you to write for me as the answer is just this one. But I want you to learn to check this at least in your head. Okay, so let us go to part B. Is this part B also following the same pattern? Yes. First of all, I have 3 terms involved. Again, 2 of them are complete squares. So if I want to do some scratch work paper, so I will just do this, for example, here. I will take, what do I do here in a scratch paper? I will take I will take the square root of the first completed square, it is 2x, multiplied by the square root of the second one, which is again 1 here. And then I always multiply by an extra 2 myself. What is the answer? The answer is 4x. And then I see that the middle term is 4x. So this means that, yes, this is the pattern. So what you need to write as the answer, you put a pair of brackets with power of 2. You take the square root of the first one, which is 2x. You take the square root of the second one. Yeah, here coincidentally it becomes 1 itself, but this time the sign is negative. So what I need to put here is this negative sign. So the answer is 2x minus 1 to the power of 2. And then any power of 2 is a product of that expression with itself. So this is indeed a product form, so it is factorized. Okay, I will not explain so much from now, I think, but if you don't understand something, please interrupt me. Okay, so part C. Here I have 3 terms. 2 of them are complete squares. So I take the square root of this one is b2. The square root of this one is 1. I multiply it to myself. It becomes 2b squared, which is exactly the middle term. So yes, this is a complete. So this is a squaring pattern. So I put a pair of brackets with the power of 2. Take the square root of the first complete square, which becomes b2. Take the square root of the second one, which becomes 1. Then I see that this middle term is positive, so I put positive here, and the answer is done. Okay, part D. So for part D, I see that I have 3 terms. 2 of them are complete squares. I take the square root of this, it becomes 3a squared. I take the square root of this, it becomes 2. I multiply them and I multiply by an extra 2. So the answer becomes 12a squared. And 12a squared is exactly 12a squared here. So yes, this is also a squaring pattern. So if I want to answer this problem, I put a pair of brackets, power 2, take the square root of this one, which is 3a squared, take the square root of this one, which is 2, but because the middle term is negative, so I put a negative sign here. Okay, and then we go to E. Of course, here in E, you see it's a little bit, the order is a little bit different, but that's not a big problem. So here still I have 3 terms. 2 of them are complete squares. Here are the first one and the second one, because this can be viewed in this way. There is no difference between this way of writing and that way of writing. Yes, these are the same. Okay, so I have 2 complete squares. I have 3 terms. I take the square root of this one is 2a. I take the square root of the other one is 3b, and I myself multiplied by 2. So what's the answer? The answer is exactly 12ab, which is the third one. So yeah, that is also following the pattern. So this becomes, I put a square, a pair of brackets with power 2. I take the square root of this one, it becomes 2a. The square root of the other one is 3b, and the sign of the third one is negative, so I put a negative sign here. But here, this is, I just want to mention that if you are in hurry, then you might make a mistake here, because you see there are 3 terms and then you see 2 complete squares. If you are in hurry, then you might say that, okay, the answer is 5x plus 1 to power 2, which is wrong. The reason is that if I take the complete square from here, the square root from here, it becomes 5x. The square root of this one is 1, but I have to multiply a 2 here, but the answer becomes 10x, but the middle term is 5x. So this does not follow the squaring pattern. But might be, this is a question that, is it possible to factorize this? The answer is that if you want to factorize this, the only possibility is to factorize it in the domain of complex numbers. So that's not a lesson. So for the lesson that we are concerning now, we say that this is a prime, it's a prime polynomial. So even if we want to work with fractions and everything, but still it's not possible to factorize this. The only way that we can factorize this is going to the domain of complex numbers, but you don't need to be worried about that. Okay, but these are more fun problems. I will give you 12 minutes. Hopefully we can arrange the time. 12 minutes is too much, but yeah, at least you can think a little bit about them. Yeah, let us give you 8 minutes, okay? Yeah, because I want to also give you some examples of conjugate pattern. Okay, so now let us start doing these. These are actually a little bit nicer problems. So here, is this following the squaring pattern? What do you think?
Well, yes, I think I managed to solve it, so yes.
Yes, yes. Yeah, because why you get suspicious, because first you have 3 terms. 2 of them are completed squares, but this is not enough. You need to check the last part. So you take the square root of this complete one, it becomes x to the 2y. You take the square root of this one, which becomes 4. And then you multiply them by an extra 2. So if I ask you what is this, you say that this is 8x squared y, which is exactly the middle term. So yes, this is the quadratic pattern. So this FG, so I would write it in this form. I write a pair of brackets with power 2. I take the square root of the first one, it becomes x to the 2y, and then the other one is 4. But because the third one has negative sign, I put a negative sign here. So what do you think about part H now?
Well, I couldn't find the pattern in it.
Yeah, a squaring pattern.
I did it, but I'm not sure if it counts. Like I couldn't get it all in the same bracket.
So
Like,
can you just yes?
yeah, for h, the answer was 2x times in bracket x squared plus 1, and that bracket is squared. So basically, I pulled out the 2x, and then you can use squaring pattern.
Yeah, exactly. That is the point. So thank you very much.
Oh.
So that was the point. And then you understand this remark now better. Because in this remark, I told you that whenever you can use your previous method, meaning pulling the highest factor out, common factor out, if it is applicable to all the terms, do this one first and then think what to do. Okay? If you follow that pattern, if you follow that remark, then that is possible. You see here, I have 3 terms, but none of them is complete a square. Either I cannot factorize it anymore, or if I want to factorize it, I need to employ the other methods. And then immediately assume that I haven't talked about the new lesson today. If I have given you this in the previous lesson, I am more or less completely sure that you were able to pull 2x out immediately. Because now the problem is changed, your brain is also thinking in a different way. So this is why I want you to understand these connections. Yes. So if I have given you this in the previous session and I ask you to factorize this, you immediately realize, because your brain was working in pulling factors out, it was easy for your brain to catch this, that 2x is a common factor. So this is why I'm saying now that remark tells you that even if you study higher levels of factorization, still that simple method has the priority over all the coming methods. Okay, so the first thing that you have to do is to exactly do what Rocco mentioned. So you see that 2x is in common, so I pull 2x out. So what is left from the first one is x to the 4. What is left from the next one is 2x to the 2. And what is left from the x1 is just 1. Assuming that this problem has 2 points, if you write here, you will get 1 point. Because this is in factorized form. It's a product of 2x and this one. But the reason that you don't get the full mark, because this part itself can be factorized more. And that is the reason that I give you 1 mark up to here. The other reason is that, can I factorize this one now? Yes, this is the new lesson. I have 3 terms, 2 of them are complete squares. If I take the square root of the first one, it becomes x squared. If I take the square root of this one, it becomes 1. If I multiply them and multiply them by 2, it becomes 2x squared, which is exactly the middle term. So you shouldn't stop here, because even though it is in factorized form, I agree with that, but it is not complete. So you write it and just write 1 more step. Both of them should be included as your solution for the problem in the exam. So then it becomes x squared plus 1 to the 2. Is that understandable now for everyone?
Yes.
Okay. And the same thing happens in part I, you see? So let me write I. Here, I have 3 terms. None of them is a complete square. Either I should ignore that and say that this is a prime polynomial, or I should find another method to solve it. And then immediately you realize there is something in common in all of them. What is that in common? What is the highest factor in common in all of them?
X.
X, just X. So just do it, okay? Because that brings you a point. I take X out. What is left from the first one is 9x squared. What is left from the second one is minus 48xy. And from the last one, 64y squared. Okay, so first of all, again, you get 1. If this is from 2 points, you get 1 point here, because this is indeed a product. So you did it partially correct, but this is not complete, because this on its own, in its own, can be factorized more. I have 3 terms involved. 2 of them are complete squares. Let us take the square root of this one is 3x. Let us take the square root of this one, it is 8y, and let me myself multiply it by 2. 2 times 3 is 6, times 8 is 48xy. And 40xy is exactly the middle term with negative sign. So this is now the new pattern. So you have to write both of them in the exam paper, in the answer sheet. So this becomes the square root of the first one, a square root of the second one to power 2. And because this middle term is negative, I put a negative here. And that is the complete answer to this problem. Okay, what about J? Do you have any idea about J? The reason that I give this example J, K, and L because I want you to broaden your point of view. These are absent in the book. I haven't seen the exercises of this type in the book, but I want you to understand because this is not something hard. Any comment that you can say on J? No comments?
Well, I'm not sure, but I got x minus 2y in parentheses minus 5 in a bigger parentheses to the power of 2. I'm
Yes,
not
exactly.
sure.
But yeah, that's correct. Because the reason that I gave you this example is because I want you to be able to broaden your point of view. Even though there are not 3 terms, these are more than 3 terms. If you multiply this, it is 2 terms on its own. If you raise it to power 2, there are 3 terms, so it's more than term. But the way that the problem writes it, it is in the form of 3 terms. 1 term, the second term, and the third term, yes? So I have 3 terms. Do I have 2 complete squares involved? Yes. This one is a complete square. It is the square of this expression. This is also a complete square. It is the square of 5. So even though this is not exactly 3 terms, but the way this is written, I can view it as 3 terms with 2 complete squares. So it might be the pattern, the squaring pattern, is it? You will immediately realize yes. So let me write this J. So I would say that, okay, so let me check it here. I take the square root of this one, it's x minus 2y. I take the square root of this one, it is 5. I multiply them and myself multiplied by 2, but 2 times 5 is just 10. And then I have x minus 2y. And then you see that this is exactly the middle term. So everything is exactly in order again. So what I need to do, I open a pair of brackets, yes, and I put a power of 2. I take the square root of the first one, which becomes x minus 2y. I take the square root of this one, which becomes 5. And then I see that this middle term is negative, so I put a negative sign here. Even though this is completely correct, but in mathematics, whenever you can get rid of extra things, you should get rid of them. So I really don't need this pair of brackets. There is no role for this pair of bracket. This pair of bracket has a role. This means that the whole expression should be raised to power 2. But there is no role for this one, so let us get rid of that. So I would write this, and then I would say that, okay, the inner pair of brackets are not necessary, so I just remove them. And then the answer is as simple as that. So x minus 2y minus 5 to the 2. So that is the answer to this problem. Okay, and now that you understood what is going on, I want to keep these 2 for the next session because I want to also give you some examples of conjugate patterns, okay? And then on Friday, we will finalize this lesson. So this lesson in the book is just 1 page, okay? But there are some examples in the book, but the topic is so important that it is really worth it to learn how to factorize and deal with these algebraic problems. So I will leave these 2 for the next session. Please think about them. And I am just writing on a school sub which pages and which problems and which videos to follow, okay? Okay, so let us go to the next page. Let me see if I can find my example. Yes. So we want to factorize this again. I am asking you distinguish for which of the following polynomials the conjugate pattern is somehow applicable. And if that's the case, factor it, okay? So for example, is conjugate pattern applicable to the first one? Is it?
I think so.
Yes.
Yes, because that is the difference of two complete squares. So if I want to write this, the intermediate step is to write, to show that 4x squared is the complete square, and 9y squared is also 3y to the 2. So you see that this is indeed the difference of two complete squares. So that is the conjugate pattern. So what I do, I open two pair of brackets. I take the square root of one of them and put them in both of these pair of brackets. The same thing for the second one. And then that is up to me. I choose one of them to be positive, the other one to be negative. So that is the answer. Okay, so let us go to part B. Do you think that B is also a conjugate pattern?
Yes.
Yes. So what is the intermediate step? The intermediate step is that instead of x4, I can imagine it as x to the 2 minus y squared. And then I can immediately see that this is the difference of two complete squares. So I open two pair of brackets. I put one of them, the square root of the first one here and there, the square root of the second one here and there, and then I choose one of them to be positive, the other one to be negative. But what do you think about part C? Is it a conjugate pattern?
No.
No, even though two complete squares are involved, but the sign between them is positive, so not a conjugate pattern. So by the way, be careful. When I am saying it's not conjugate pattern, I am not claiming that this is not possible to factorize it. But I am telling you that at least if you want to factorize it, conjugate pattern will not work. And I told you that the lesson of factorization is a hard one. If you want to follow, you can see some of my videos and follow them. But this is at the level of your book is enough. Okay, now again, I want to see how many of you can give me this as the correct answer. What should I do here? Is it in this form a conjugate pattern? Is it or not?
I'm just gonna say yes.
Is it a conjugate pattern in this form?
Yeah.
No. What? So
Okay.
because this, even though this is the difference, but why do you think that this is a complete square?
No.
No. So this is not a difference of complete squares. Either we should ignore that, or the important thing is again this remark. Okay. Again, you see, you need to take lesson from your mistakes. If I am completely sure, if I have given you this example in the first session, you would immediately give me the correct answer, at least partial answer. So why don't you follow that? Remember again, let me emphasize, this remark tells you that the first technique that we learned, pulling out a factor out, if applicable to all the terms, has the priority over any kind of method that you will learn, okay? So here, you see that what is the common factor between these two?
Both
is
x and y.
So I take xy out first. At least you get 1 point here because you factorize it, yes? This is in the product form, but it is not complete. Why? Because this factor in its own can be factorized more now using the conjugate pattern, yes?
Yes.
So what happens? It becomes xy, and then I write x minus y without the explanation. I think it's easy. So this is the where that you have to stop.
Yes.
This is the complete factorization of this expression. Is that clear?
Yeah.
Okay, let us go to part E. So part E, I have this expression. Can I use the conjugate pattern here? The answer is yes. I have the difference. X4 is a completed square, Y4 is a completed square. So let me write the intermediate step. So X4 can be viewed as X to the 2 to the 2 minus Y to the 2 to the 2. But then immediately I realize this is a conjugate pattern. So I take the square root of the first one, I put it here and there. I take the square root of the second one, I put it here and there. And then I put a negative sign. One of them should be negative, the other one is positive. Do you think this is the end of the story, or should I continue? Is it the end or not?
You should continue.
Continue. How? Here, yes?
You can add a power to.
Add a power to you. What do you mean by add a power to?
You should square it one more time to get the power of 4.
No. No, so be careful. If you do this the other way around, you will reach to the first one. No, so this is very important to understand so this is, I am not asking you to find the answer to this, because the answer to this is again this one. And this one, you see, by the way, this is a very good way. Let me just continue. This is not complete. The reason is that this factor in its own can be factorized more, because this is again a conjugate pattern. So there is no X4 involved. So I will put a pair of brackets, 2 pairs of brackets for this one. And I factorize it using the conjugate pattern. So it becomes X minus 1, X plus Y, X minus Y, X plus Y. And then for this one, I cannot do anything, because this is the sum of 2 completed squares. Sum of 2 completed squares is not the conjugate pattern, so I cannot factorize it anymore. So I have to copy and paste it like this. So you see that if I give this in the exam and ask you to factorize this, this up to here is 1 point, and then continuation will bring you another point. If you stop here, this is a product form, I agree, but this is not a complete factorization, because one of the factors can be factorized more. By the way, let us mention something here. Here, the goal, let me emphasize again, is not simplification. Which one is more simplified? Do you think that this is simpler than this one, or the other way around? Of course, immediately it is clear that X to the 4 minus Y to the 4 is a more compact and simplified version of an expression. So here, the goal is not making something more simpler. Actually, you see that I am not making it simpler. Actually, I'm writing it more complicated. X to the 4 minus Y to the 4 is easier for our eyes, for our brain to work with, instead of this one. But the reason that this is useful, and we will see why this will come useful in the future, is that this expression is not in the product form. It is the difference of 2 expressions. But now this expression, even though it is equal to this one, but it is in factorized form. So please pay attention to these very small points. Okay?
Babak,
Yes?
I didn't quite follow on the number either. So you might have explained it, but I don't think I understood. Why is the third bracket not in a conjugate pattern?
No, because the conjugate pattern is the difference. Here you see, I have emphasized on the word difference.
Yeah.
If I have the difference of 2 completed squares, it's a conjugate pattern, yes?
Okay.
It's the sum of 2 completed squares.
Okay.
Okay, and that is exactly why this was not a conjugate pattern. You see, the answer to part C, I wrote it is not a conjugate pattern. The reason is that because here, this is the sum of 2 completed squares. Okay.
All right.
Okay, so you see that 1, 2, 3 items here is left, and then 2 items here is left. I really want you to think about them. You will not learn mathematics by just not doing exercises. You will learn them by doing exercises. And then let me also add one problem here, if I can find it correct. That is also good to think about this one as well. Yeah, so I will also write, oops. Yeah, it's hard to catch it here. So I can put it here so that if we need enough space for the other parts. I will come back to these questions, but the point is that it is better you think about the problems first, and then when I solve them, you will learn them better, okay? So on Friday, I will finalize this lesson. It was just one page, as I told you in the book, but this is very, very important. So this is why I'm emphasizing on it, and then we will move on, okay? Any questions?
No.
Okay, and then by the way, I told you that when I upload these videos to the YouTube channel, below the video, you will find the link to the PDF file of these notes. Of course, the notes will also be uploaded on Google Drive. So which one is easier for you, you can choose. Okay, I will stop